Why, hello, advanced geometry students. It's Mr. Donaldson coming at you live. Well, actually, this is not live. Coming at you virtually, maybe that's better, for section 6.2. Today we're going to talk specifically about chords. And before we get into that, though, let me remind you of the definition of a chord. Just remember, a chord is any segment whose endpoints are on the circle. So, for instance, segment AB is a chord, segment FD, segment DE, segment BE, those are all chords. All right, and we're going to, all the theorems today just kind of reference chords. So, before we get into that, let's just go through and talk about the difference between what an inscribed angle is and a central angle. All right, central angle we already defined. A central angle is an angle whose vertex is at the center of a circle. I thought my handwriting would start to get better, but it's not happening. So, for example, in this picture, angle BCD is a central angle. And I'd like for you to try to list some other ones. So maybe pause here and list the other ones. Okay, welcome back. Angle ECD is another central angle. Oops. ECD. Angle FCD is a central angle. And let's see, maybe there's one more, angle BCF. You'll notice in order for it to be a central angle, the center of the circle C needs to be listed as the vertex or in the middle of my angle. So there you have it. An inscribed angle is a little bit different. It's an angle whose vertex is on the circle. So here's the first example I gave, angle ABE. Look at angle ABE right here. Its vertex is on the circle. So there's a couple more in this diagram. I could say angle FDE. That's another inscribed angle because its vertex is on the circle. And then there's also this one, angle BED. So you got to know the difference because, in the directions of a problem, it might be like inscribed angle ABC. And you would need to know that that point B, the vertex of the angle, is on the circle. And one other thing I wanted to remind you of before we move on today is that in a circle, all radii are congruent. So as soon as I see this diagram, the very first thing I would do, I would mark all my radii congruent. Because that could be helpful. Like, check it out. Right now I know that this is an isosceles triangle. So technically, these angles would be congruent to each other. So it's really important that you mark that so you can see what else is true in the diagram. All right, so the first theorem about chords today is that if two chords in a circle are congruent to each other, then the central angles that intercept them are congruent. So what I'm saying essentially is that in this picture, if I know that segment AB is congruent to segment CD, that's given, right? Then I can justify that angles 1 and 2 must be congruent. And this is a really easy thing to prove. Check this out. I know from the given that AB is congruent to CD. I also know from what I just told you that in a circle all radii are congruent. That means AE is congruent to EB. Actually, why don't we do it like this? AE is congruent to EC. All radii are congruent. And EB is congruent to ED. Well, guess what? That means these two triangles, triangle AEB, has to be congruent to triangle CED because of side-side-side triangle congruency. And if the two triangles are congruent by side-side-side, then by CPCTC, I know their corresponding parts are congruent, and that will make angle 1 congruent to angle 2. So again, it's really important, I think, that you guys see the justification for all these theorems, and remember that when something's called a theorem, that means we could totally prove it. And most of these proofs are going to come from triangle congruency. That's why we spend so much time with that. All right, the next little thing today is just some definitions. So first, an arc measure. So let me erase this stuff so we can talk about it. The measure of an arc is equal to the measure of its central angle. So what that means is like if the measure of angle CED was 50 degrees, that means the measure of arc CD would be 50 degrees. The central angle is equal to the arc measure. And I think we talked about this in the last unit as well, last section as well. All right, and then next, congruent arcs. Congruent arcs are just simply arcs that are in the same circle or in congruent circles that have equal measures. So like arc CD, and then if I put a 50 degree over here for arc AB, then I'll be like, oh, those are congruent arcs. They're in the same circle and they have equal measures. And then the last thing on this little page is if two chords in a circle are congruent, so just like this diagram up here, then their intercepted arcs must be congruent. So in this diagram, if I know that AB is congruent to CD, which it totally is because they're marked congruent, that means that those chords, or excuse me, those arcs that are intercepted by those chords are congruent. So if AB is congruent to CD, that means arc AB has to be congruent to arc CD. And that'd be really easy to prove from this theorem, because if the central angles are congruent and the arc measure is defined by the central angle, well then the arcs would be congruent as well. All right, so let's do some examples. All right, use the two theorems that we just saw to solve for the variables. So this time I want to solve for x. All right, now remember, the very first thing I said you always want to do is in any circle, mark your radii congruent. And the reason that is so important is because now I can see that this triangle is isosceles, which makes this 50 degrees because the base angles need to be congruent. That 50 is not so good. Let me try that again. And then by the triangle sum theorem, if 50 and 50 is 100, that leaves 80 degrees here. And then by using the theorem we just learned, if in a circle the chords are congruent, then the central angles that open up to them must be congruent. So x must be 80. All right, in this next example, I also have congruent chords again, but quickly I'm going to mark that I have my radii congruent. Now, this time I want to find y. Now, y is this arc measure. Now, remember what we defined an arc measure to be, and that's equal to the central angle measure. So if I could find this central angle measure, I would know the arc measure. Or, if I have congruent chords, that means I have congruent arcs, which means if I know arc AB, that would have to be the same as arc CD. And check it out. Here's what I know. This is a straight line. This is 70 degrees. That leaves 110 degrees here because they add to 180. And a central angle defines an arc's measurement. So this arc will measure 110 degrees. And if two arcs, AB and CD, have congruent chords, segment AB and segment CD, then the arcs themselves are congruent. So y will be 110 as well. All right, and here in this last example, if AB is congruent to CD, it's time to kind of overlap, so let's just focus on them. So this segment is congruent to this segment. We want to solve for x. All right, now check it out. Remember, congruent arcs have congruent chords. So this is what I know. I know that arc from D to C, arc DC will be congruent to arc AB. Both of those minor arcs would be congruent to each other. And because they share 30 and they overlap 30, I could deduce that x would be the same as arc CB. So in this specific case, because this arc from C to D has to be congruent to this arc from A to B, and this part overlaps, x's, or these two arcs, AD and CB, could both be represented by the same variable, or x. So all the way around the circle is 360 degrees, so simply 90 plus 2x plus 30 is equal to 360. So 2x is equal to 90 plus 30 is 120. If you subtract 120 from both sides, that's 240. So x is 120 degrees. Or the degree symbol's already there, so we can just say x is 120. Because when I substitute 120 in, I'll get degrees. Sweet. All right, so the next one's called the perpendicular to a chord theorem. A line that is perpendicular to a chord and contains the center of the circle must bisect the chord. So, given this diagram and this statement, here's what's given to me. A line that is perpendicular to a chord. So, I'm going to be given that line AC is perpendicular to line BE. And I want to prove that it has to bisect the chord. So I want to prove that segment AC bisects segment BE. So just to oversimplify what that means, I need to show that BD is congruent to DE. And the way I'm going to do this is by simply using triangle congruency. All right, so check this out. I'm going to draw two radii. There's that one, and there's that one. And I know for sure that in a circle, radii are congruent. So that means that BC would have to be congruent to CE. I also know that these two triangles, BDC and EDC, share a side. I know that DC is congruent to itself. And then just by looking, you guys, if I look at these, it kind of looks like ASS, right? Here's my angle and then the side and the side. But remember, if they're perpendicular, then these are right angles. And if those are right angles inside of a triangle, those are right triangles. So I know triangle BDC and triangle EDC are right triangles. All right, I got right triangles with congruent hypotenuse and congruent legs. Those triangles are congruent to each other. So triangle BDC would have to be congruent to triangle EDC because of HL triangle congruency. And then finally what that means? That means that BD is congruent to DE, which would mean that D is the midpoint of segment BE. And by the definition of a segment bisector, it's just a segment that contains the midpoint of another segment. That would mean that AC bisects segment BE. And again, you guys, I know we're just kind of very informally talking about the proofs of these things, but it's really important that you understand that you can prove them, but we're being pretty informal about how we justify it. But look, just by given that that's perpendicular, I was able to deduce it has to bisect it. All right, a couple more theorems. The chord distance to a center theorem. Two congruent chords in a circle are equidistant to the center of the circle. And I'll show you an example of that in just a second. But if chords are the same length, they got to be the same distance away from the center. And the closer a chord is to the center of a circle, the longer it is. Right? So here's the center. I got a chord that's very far away, and I got one that's really close. The closer chord to the center would be longer. Right? And the perpendicular bisector of a chord theorem says the perpendicular bisector of a chord always passes through the center of a circle. And here's what that means. If I wanted to find the center of this circle, I could draw a chord, and I can create a perpendicular bisector of it. And then I could draw another chord, and I could create a perpendicular bisector of that one. And I know my drawing kind of sucks. But those two would have to meet at the center. This is a pretty useful theorem, and I'll show you an example in class, because you could find the center of any circle by using this theorem. All right, so here are just a couple quick examples. All right, so in this specific case, here's what I know. I know if this central angle is 140, its arc is 140. And I know that all the way around a circle is 360 degrees. And look, if these chords are congruent, that means their arcs are congruent. So I'll just do 360 minus 140. That's 220 degrees left. And since these chords are congruent, that makes each one of these 110 degrees. And then, of course, the measure of an arc is equal to the measure of its central angle. So both x and y are 110 in this case. All right, in this problem, solve for the variables. First of all, congruent chords, BA and DE, have congruent arcs. So that means that x is equal to 90. And then if this is 90 and all the way around the circle is 360, well, 360 minus 90 minus 90 minus 70 is 110 degrees. So y is 110. All right, and I'm about to be out of time, so just real quick for this problem, you would just set x squared minus 6 equal to 5x and solve by factoring. And as soon as you figured out what x is, you could plug it back in and determine what y and z are. All right, and then over here, which one is the center? Now remember, a perpendicular bisector of a chord contains the center. This is perpendicular, but not necessarily a bisector. This is a bisector, but not necessarily perpendicular. So it's not B. A will be the center. because it contains two perpendicular bisectors of chords. All right, we can talk about 3 in class. Have a good one.